All right, hey, getting a late start on this. It's like 8:30 already, but I fixed my computer. You guys would be so proud of me. So tech savvy. You know what I did? I updated the graphics card drivers. Pretty cool trick, huh? Anyway, I'm gonna try to go fast. I'll probably split this thing in two. I told at least one kid that I'd try to get something up by 9. So I'm just going to record for like a half an hour and then post whatever I have. And then I'll record more and post that too. So that way by 9 you'll have something at least to start watching. And I feel like that probably means I should work backwards. So I'll start from the solving equations stuff. That's probably the stuff that you guys are still the most iffy on, and we'll jump right to lesson 5, where the hardest ones are, I guess. Um, and I won't do the hardest thing first necessarily. Let's just grab a problem and do it just to make sure you guys are okay. And I'm just going to grab a random one. I don't feel like I've done 27, so let's just do 27, which is pretty easy, but still, it's a good one to just start on. So this is 27. So 27 is good because you don't actually have to do any algebra. You're just ready to solve. So let's just talk about the basics of how do I even figure out who's in my solution set, how do I express that solution set, if I want an infinite set, and how do I... Oh, rats. Geez, my little tablet's messed up. Hold on, let me try to fix that. I fixed it. Can't call me a boomer. Nope. Totally understand technology. Okay. So anyway, you're looking to figure out when cosine equals negative root 3 over 2, right? So you've already isolated the cosine expression. You're down as simple as you can go because you can't do anything with the 4. We know that we deal with the 4 after we found our solution set. We kind of deal with the 4 by, in a way, just doing a U substitution. I don't know that anyone literally does a U substitution, but in your head you're thinking, why don't I first find the solution set for U and then just go through and divide by 4? So that's what we'll do. So I still really prefer drawing a picture. Maybe you guys don't. Maybe you guys know off the top of your head which angles have cosines of negative 3 pi or root 3 over 2, but I don't. And I don't ever want to know because I always can draw a picture and I feel safer doing that, so that's what I'm going to do. But I'm looking for x coordinates of negative 3 pi over 2, so that's x's that are left. It's x's that are very far to the left. So that tells me I want these positions, and that tells me I'm looking for 60-degree reference angles. I'm looking for those two positions. Let's let one of them be blue while the other is orange. And you guys know that you absolutely may write two separate equations. You could write me one equation where the blue angle is 5 pi over 6. And then you have to add to that the distance between this blue angle and the next blue angle, which of course is a full rotation, so 2 pi, times k. And of course k would have to be an integer. Now you can just write another equation, an orange equation. So instead of starting at 5 pi over 6, we'll now start at 7 pi over 6. And we'll add to that 2 pi k, where k is an element of the set of integers. And this right here would be the solution set for u, but of course u is actually equal to 4x. So if you're trying to solve for x, you'd have to divide through by 4, or maybe more obviously multiply through by 1/4. And so x is actually going to be 5 pi over 24 plus 2 pi over 4, which is pi over 2, times k, where k is an element of the set of integers. And we want all the orange guys too. That'll be 7 pi over 24. Plus pi over 2 k, where k is an element of the set of integers. So there's your solution set if you were supposed to give me every single possible answer. Now, if you were supposed to give me a solution set that was finite and that only included the elements that were between 0 and 2 pi, then we said that what you do is you basically, well, you let k take on all the values of all the integers. So, 0 is a pretty obvious starting point. If I let k be 0, then I get 5 pi over 24 plus, well, 0. So 5 pi over 24 is in my solution set. I'm leaving a little room because maybe, just maybe, there's some wiggle room for there to be another angle that's less than 5 pi over 24, but still greater than 0. I don't think so. 5 pi over 24 is pretty damn small. But there is a chance that, well, k is supposed to be an integer, and I just started at 0. But -1 is an integer, and so is -2. But if I let k be -1, then I'll be subtracting pi over 2, and I'm way up here now. 5 pi over 24 minus even the smallest possible deduction, even the smallest thing of pi over 2, that's 12 pi over 24. So even that first subtraction of pi over 2 is going to push me into the negatives and give me an angle that's too small. Now on the other hand, 7 pi over 24 is bigger than 5 pi over 24, so maybe I could subtract pi over 2 from it. If this was 7, is that good enough? Well, no. That would still be -5. I'm still negative. So 5 pi over 24 and 7 pi over 24 are definitely the first two correct answers that I get in my interval. And then from here, I just like to just keep pushing forward until I start getting answers that are too big. And if we're talking about pi over 24s, then 2 pi is technically 48 pi over 24. So that's a pretty high bar. Like, we're going to get a lot of answers, but maybe we ought to know we're going to get a lot of answers. No, we're not going to get that many. All right, let's keep going. So what am I adding on to get the next one? Well, we're adding on pi over 2. So remember, we just said that -1 gave us negative answers. -2 is going to give us negative answers. Any other negative number will give us negative answers. But 0 gives the first couple. 1 will give the next couple. So let's add pi over 2. And pi over 2 for us is going to be, well, we're multiplying by 12 over 12. So it'll be 12 pi over 24. So if I add 12 pi over 24 to the 5, then that'll map me forward onto 17 pi over 24. So we're not going to get that many answers because we are jumping forward by kind of a big amount. If I add 12 pi to the 7 pi, I get 19 pi over 24. But there's still room for more. So let's just keep adding on. From the 17, we can add on another 12, and we'll get 29 pi over 24. And from the 19, we can add on 12 more. That brings us up to 31 pi over 24. Is there room for more? Let's add another 12. 12 would bring me up to 43. That is less than 48. So 43 pi over 24 is in our set. And how did I get that? I blew it, actually. I blew it. I shouldn't be adding on to the 31. I need to go back and add on to this. We are kind of getting our answers in pairs, right? So we're getting these two that are close together. Then we jump forward by pi over 2, and we get these two. Well, so I did blow it. So then the 29 and the 31 were another pair. I needed to add on to the 29, which gives me 41. Yeah, so 41 pi over 24 first, then a 43 pi over 24. And now finally, if I try to add on another 12 pi over 24, I'll be too big. So this would be it. We end up getting 8 answers, sort of 2 at a time. This would be our solution set. And one nice thing is, I don't think any of these reduce. I think every single numerator is prime. 5, 7, 17, 19, 29, 31, 41. Yeah, so I think that solution set will do it. And I see that a little bit of that solution set is hidden behind my face. But not anymore. So there you go. I do think that as you study tonight, you are probably going to want to just practice giving your finite solution set on that window that goes from 0 to 2 pi, and also practice giving me the infinite set. Don't worry so much about combining these into combining the two equations into one super equation. That's just not as big a deal as I think I might have made it out to be. But for those of you who, really wanted to, of course, the way you would do it here is you would just recognize that these two angles are the opposite of one another. This blue guy is 5 pi over 6. And we can just think of this orange guy as negative 5 pi over 6. Which means I can get rid of the need for this entire equation right here by simply sticking a plus or minus on the blue 5 pi over 6 that we had. So, because it's so easy to modify our two equations into just one equation, it's probably worth it for this problem to do that. But I wouldn't go nuts. I wouldn't break my back trying to make some fancy expression just to turn two equations into one equation, right? It's just not worth it. So just do what you're comfortable with, and it doesn't matter. Hopefully that was helpful to somebody, but even more helpful would be if I jumped ahead and looked at a much more complicated problem. So let's try to find one. I don't think this problem set has any that are all that complicated. So we may have to jump to the next problem set. Yeah, because these are all pretty straightforward. As I say that, I'm looking at the bottom couple, and a lot of people approach me with questions about those, but I can say with confidence that you just don't need to know any of these where there's that phase shift involved. It's not hard, really. It's not that hard to deal with, but it's not on the quiz, so don't spend any brain power on it. Let's look at the next batch of problems. Now these are more interesting because these actually do require a bit of algebra at first. Now when I say a bit of algebra, something like number 7 is so little algebra that it's not even worth talking about, because it's 2 cosine x plus 1 equals 0. The quote-unquote algebra that you have to do is subtracting 1 and dividing by 2. And you land on cosine of x equals negative a half. And so now this green equation, that's pretty much exactly like the problems from the previous problem set that we just said were, fairly easy. It's even easier than these because these actually have the multiple angles in them. But I'm not going to waste my time, I don't think, on something like 7. But I do see something ever so interesting. I'm not sure we spent a lot of time on these squared ones. So let me just grab one of those and do it super fast. Something like 12. So 12 says tan squared of x equals root 3. Oops, I'm getting ahead of myself. It just says equals 3. But since this is tan squared, the first thing you'd want to do is take the square root of both sides. And the one thing I want to make sure that you all remember is when you solve an equation by taking the square root of both sides, you have to consider the positive root and the negative root. That's obviously a big deal here because when I go to consider my solution set, if you forgot the plus or minus, then the places where tangent equals positive root 3 are the 60-degree angles, right? So pi over 3 here and a pi over 3 reference angle here. But we don't have to be positive root 3. We can be plus or minus, which means we actually want the 60-degree reference angles from quadrant 2 and 4 as well. So there's now 4 different positions on the unit circle that should be part of our solution set. We've got the pink and the orange and the green and the blue. So okay, here, how many equations should you write to model the solution set infinitely? If you wanted to write 4, you could. And if you were going to write 4, you would write pi over 3 plus 2 pi k. Then you'd write 2 pi over 3 plus 2 pi k. Then you'd write 4 pi over 3 plus 2 pi k. And 5 pi over 3 plus 2 pi k. But hopefully you get that that's silly. A pretty easy way to boil this down would be, think of the pink and the green as a pair. Those are pi radians apart. So surely I can do all the purples together by just doing the 1 pi over 3 plus, well, don't add on 2 pi k, add on 1 pi k, where k is an element of the set of integers. Then you can think of, well, I already used the yellow. The yellow and the blue are just the yellow and the yellow. And I can kill all the yellows in one fell swoop. Now yellow's not going to show up unless I make the background lavender. Then maybe we'll see yellow. But it would be what now? Well, this position is 2 pi over 3. I don't know why I'm so bad at this. Oh, that does not show up at all. But it would be 2 pi over 3 plus pi k, where k is an element of the set of integers. So there's a second problem. That's too dark. That's an okay, whatever. Anyway, that's your infinite set. The moral of the story boils down to, when you've got one of these guys squared, just remember that when you take the square root, it'll generate a positive root and a negative root. The instructions here were find all solutions, but I do still think it's worth it to also give the finite set. So just super fast. This one's kind of easy. If you were going to give me only those solutions that lay between 0 and 2 pi, pretty obviously we're taking the pi over 3 and the 2 pi over 3. And then we're adding pi. Well, this one's easy. It's not a multiple angle one, so we can literally see all 4 answers on the grid anyway. So maybe this was a waste of time, but we're adding pi, so adding 3 pi over 3 would map us forward to 4 pi over 3. Then if we add pi to 2 pi over 3, then we're adding up to 5 pi over 3. And so that would be your finite set. This is your infinite set. And that's another one in the books. Let's do an even harder one. Is anything on this page worth doing? I don't know. I mean, 19. We should probably have a talk about 19 again. I say again, we've never talked about it, but we sort of have. We did number 19's easier cousin. Didn't we have one that just said, we had sine of 3x equals cosine of 3x. And how did we deal with that? We talked a lot about that problem. We said that you should probably be thinking that you should divide through by sine or divide through by cosine. We talked about how dividing is typically dangerous. You don't want to do it. You want to subtract from both sides first instead to get it set equal to 0. And then instead of dividing, you want to factor out, which kind of feels the same as dividing. Now I like tangent, so if I factor out cosine, I'll get a tangent. If you like cotangent, then you can factor out sine and you'll get a cotangent. But I prefer tangent, so I'm going to choose to factor out a cosine factor. Then that forces this sine, when I factor out of it, to become a sine over cosine, which is tangent. And then the cosine, of course, would be minus 1 equals 0. I could go from there. Hopefully, as you guys look at 19, you're feeling like this is probably going to follow a similar approach. I'm not going to divide through right away. I need to subtract and get it set equal to 0. When I do divide through, I'm not going to divide. I'm going to factor. And I'm going to factor out a cosine squared. So I'm suddenly going to have a squared to deal with. So let me erase this old guy. And hopefully just you remember doing this one. And hopefully you see how similar this one is. So let's do it and see what the differences are. We're definitely going to do that thing I just said, which is subtract this from both sides. So we now have a sine squared x minus 3 cosine squared x equals 0, which means I can now factor out. I still like tangents more than cotangents, so I'm going to factor out the cosine squared. And if I factor that out, I generate the same sine over cosine, which I can just treat as tan squared. And here I'm left with a 3. So I've got my two factors. All right, again, time to have that talk. So by not dividing away the cosine, I now still have cosine as a factor. It's cosine squared, and it equals 0. And if I was to solve this and find all the values of x that make cosine equal to 0, would they all end up being extraneous, or would they all end up being real solutions that I need? Well, hop back up here. Isn't tangent sine over cosine? So tangent's going to be undefined when cosine is 0. So this is, again, one of those situations where I could actually go ahead and just kind of dismiss this factor, because all of the solutions here are definitely going to be extraneous! Exclamation point. But maybe you should do at least this to show me that you're thinking about that higher level algebra, and that you're doing the safe work of factoring it out, considering it, but then dismissing it because the solutions are extraneous. Okay, great. But now, this other guy, this tangent equation, he's going to generate our actual solutions. We're going to get a tangent squared minus 3 that equals 0, so obviously you'll add 3 to both sides. Then you'll take, is that exactly the one I just did? It is, isn't it? Didn't I just say? So I don't need to waste time on this now. Yeah, we just did number 12. That's now the exact factor we're working with. So if you want the solutions, just rewind the video, because we're in the same spot now. Hopefully you see that we're in the same spot. We would take the square root. We would get tangent of x equals plus or minus root 3. Again, I don't need to consider this garbage anymore. So my solution set is now the exact same set that I had before. Anyway, hope that was helpful and not a waste of time. I have 9 more minutes until it becomes 9 o'clock. So I'm going to try to do one more problem. Let's find a good one. Are any of these good? I don't think so. This one, like something like 20 that's already factored for you, you would just immediately rip the two factors apart, set them equal to 0, and you'd solve the two mini equations by adding 1, dividing by 3, taking the square root, or adding 3, dividing. I know somebody out there is probably screaming, hey, can you just do it, please? But no, I don't want to. So let me look at a harder one. Probably something like 21 looks pretty nasty. We didn't do anything like that, did we? 21 looks great. Let's do a 21 in the 9 minutes I've got left. And like I said, I'm going to post a part 1. There'll be a part 2. And in the part 2, I am going to go back and talk about the graphs of the inverse functions. You probably forgot about that, but it's in the packet and you got to know it. So you better review those graphs and their properties, like their domains and their ranges. I'm going to go back and we're going to just evaluate the simple expressions like the quiz we took. Everybody has that quiz in their possession, except for you, James. Sorry, forgot to give it back to you. But you guys should be studying those problem types because they're going to be on the quiz again too. And then, of course, there's the solving equations, but it's kind of only 3 objectives. So this first part of the video will be focused on solving equations. The next part, we'll go back and look at the graphs of the inverse functions and their properties. We'll look at evaluating expressions, and then you'll know everything you need to know. Hey, how do you solve 21? Well, I see a cosecant, and I see another cosecant, and again, my heart says, why don't you just divide by cosecant on both sides and make it cancel out? But holy cow, I would say the central theme of this week has been, don't do that. You guys know that we're not going to divide anything and make it go away. We're going to factor it out and just bring it to the front. So if I factor out a factor of cosecant, then I'll be left with a factor of secant minus 2. And I'll go to solve this. So if I say cosecant of x equals 0, that's going to give me some solutions. And if I go secant of x, sure, minus 2 equals 0. So this guy's already solved for us. We just want to know when does cosecant equal 0. But wait, this is a trap. Because cosecant, isn't cosecant the reciprocal of sine, and doesn't sine pass through the origin, and doesn't sine go up and down and up and down and up and down and up and down? That's sine. So cosecant is this guy with the asymptotes and the reflected thingamajiggers. And they're asking you, when does that pink guy equal 0? Well, the answer is never. 0 is in the middle of all these little humps. This thing has no solution. And if you stop and think about it a different way, graphically it's obvious that cosecant never equals 0, but algebraically, and based on the definition of cosecant as the reciprocal of sine, they were basically asking you, when is sine equal to the reciprocal of 0, which is 1 over 0? They were asking you, when is sine undefined? Sine is never undefined, right? Sine doesn't have asymptotes or holes or anything. So either way you think about it, when does cosecant equal 0? It never equals it. When is sine undefined? Never. So what solutions does this blue equation bring to the party? None. So forget about it. Solve this guy instead, because I'm pretty sure that secant does equal 2 sometimes. And the times that secant equals 2 are the same as the times when cosine is equal to a half. So you just solve. We're back to a pretty simple thing again. Cosine is x's. X's are 1/2 at 60-degree angles to the right, so here and here. And then we're done, right? Once you know that you want those two positions, and there's not a multiple angle here to deal with or anything. So this should be cake, and it's a nice plus or minus one too. So I can pretty easily write a single infinite expression that says that x is equal to pi over 3, and also negative pi over 3, so plus or minus. And then I'll add to those two angles, of course, full rotations of 2 pi. So that equation represents every single possible answer. All right, I'm just going to try to be a man of my word. It's almost 9. I have really not covered everything that you need to know, even about equations. Like there's probably some other tricky thing. But let me post this little half-hour video so you guys can start watching that. And then while you're watching it, I'll make another that you can watch when you're done, if you want to. All right, thanks. Goodbye.